All right, so there were some problems on the homework from Module 6, and also getting a little bit, it relates to Module 7 as well, about sampling and experimentation. And so there was an example in which you have to recognize what's a simple random sample. And I'm going to do a different example, very similar here, to try to clarify that. So you have a cafeteria. It has 6 students sitting at each of 4 tables. So you have 24 students in all in the cafeteria. And in this diagram, I've given some of them names, and others I've just put dots there for students because I didn't want to make up 24 names. And so what is a sample of size 4? So one vocabulary misunderstanding that comes up reasonably often is people will say, okay, well, a sample, it's like Bob. Bob's a sample. No. A sample in this case is a set of 4 students. Our plan is to randomly select 4 people to try to represent the larger population. So this is like in your project where you randomly select 36 counties in the United States to try to represent all 3,000 counties. And you just hope you get a variety of counties that is like all the counties in some way. I'll talk more about that later, what is a representative sample. Okay, but so each one of these sets of 4 students that I've written down here is an example of a sample of size 4. One sample contains 4 students. And there are hundreds of ways that you could pick 4 students. Now, a method of getting a simple random sample. Simple random sampling method. It's a technique that makes all the samples equally likely to be the chosen sample. What do I mean? Out of all possible sets of 4, every set of 4 has to be just equally likely to any other set of 4 to be the selected set. Now, is this, I'm not saying it is, I'm asking the question, is this a way to get a simple random sample? You go around to each table and you roll a 6-sided die and it tells you which student to pick from that table. So you get one person by rolling the die at table A, you get another person, you roll the die at table B, you go around the room, you get 4 people. Is that a simple random sample? What do I mean? I mean, does it make all possible combinations equally likely to be selected? Well, a rhetorical question. I'm just recording, but no. Why is it that not all samples are equally likely? Well, look at this first one here. It's a perfectly legitimate set of 4 people from the class, but you'll never get that one. Because when you go to table A, you roll the die, you pick one person, so you can't get Bob and Sally. Not possible. On the other hand, this one down here at the bottom, where you have Bob and Jane and Karen and Jim, that might happen. It's a small chance, but maybe, you go to table A and you get Bob, and you go to table B and you get Jane and Karen and Jim. So some of these samples could occur, others would be impossible. So they're not all equally likely. So that's not a simple random sample. What you'd have to do is put all the names on popsicle sticks in a box and shake it up and pick out a name, and then shake it up and pick out another name. And that way you get a simple random sample, because all combinations are equally likely. Okay. Well, we have a small live audience for the recording. Did anyone want to jump in here with a question, or are we good on that? Not seeing anything, so we're probably okay. All right.
I'm good on that. Sorry, I was muted.
Well, that's no problem. Thank you. Okay, so now I'm going to do the next thing. So what's the difference between a biased sample and a representative sample? In a representative sample, every variable is distributed in the sample as it would be in the population. What do I mean? If 12% of the population is left-handed, then 12% of your sample should be left-handed. And if a certain percentage of your population is between 5 and 6 feet tall, you got to have the right proportion of that in your sample. I mean, if it's going to be perfectly representative. And that would have to be the case for all the variables, which is a problem because you can't even think of all variables. I mean, you know, a person has infinitely many characteristics, so we can't even list all the variables, never mind make sure the proportions are right for all of them. So a perfectly representative sample is hard to come by. Okay. But a hint is you don't do it by trying to list all the characteristics and get it right. You use random selection. Because if you get 1,000 people, we'll do probability calculations later, but the probability of getting the correct proportion of left-handed people is very high. At least you won't get very far off, just by chance. It comes out like that. There are only a few samples that give you, a different mean, a different average from what the whole population would. And so that's the idea. We'll use randomization to accomplish a representative sample. Now, a biased sample is just not that. It's some variables that are represented are differently distributed in the sample than they would be in the population. So you get the wrong proportion of left-handed people, for example. Okay. Now, there were 2 problems in the homework that many people missed. I probably didn't talk about it enough. I would have. Scolding the class here. Nobody showed up for the Zoom on Wednesday. Okay. So, let me switch over here to this worksheet from the homework. And question 5 here is one that we need to talk about. So an instructor is going to do this experiment. The instructor has made up 4 different worksheets to cover the same material and wants to find out which one of them gets the best results from the students. And so he wants to put the students into 4 different, what you call treatment groups. That language is from Module 7, but just 4 different worksheets, let's say, 4 different circumstances that you try to see what's the difference. And so what's the best way to like distribute the students into the 4 groups? Well, you could do it as people come in the room. First 10 people get worksheet A, and the next 10 people get worksheet B, and so forth. And then they all do the worksheet, and they come back a few days later, you take the test, and find out maybe which worksheet was better. That's a terrible way to do it. I mean, I don't know, maybe this classroom is right next to the gym, and the first 10 students who come in are the ones, you know, who've just been exercising for the past hour, and so they come in and they're all tired when they do the worksheet. Or else they're all amped up when they do the worksheet. I don't know, but maybe it makes a difference. Okay. Or, let me skip down to C. Oh, yeah, I was just talking about C as people come in the room. Okay, walk in the room. In A, it was, you go down the class roster. Okay. So what's wrong with that? Well, like everybody whose name starts with a Z is going to get worksheet D, you know, the 4th treatment. Maybe that matters, maybe it doesn't. I don't know, you're going to get extra people, either of East European origin, like Zbigniew, or you're going to get a lot of Chinese names, like Joe. So that might or might not make any difference, but the point is, you want to be able to prove that it's the worksheet that mattered and not something else. And so with either treatment A or C, you're vulnerable when you finish the experiment and you wrote up your paper and somebody looks at it and they say, well, you know, how do you know it's not just the gym next door? Or how do you know it's not just, you know, that something about first language that you spoke or ethnicity going with the letter of the name? And so, and you can't prove that it isn't. Okay. But if you do it with a random assignment, at least you're not building in any potential bias. Okay. Now it might happen just randomly because with such a small group, 10 students, with such a small group, the randomization is not guaranteed to even everything out. It's only when you have a real big sample that that will happen. So B is the best approach here, but it's not great because of the sample size being too small. And so those are, you know, the issues that we'll come to as we move into the probability part of the course. But what you just need to know now is a randomized experiment takes all the subjects and randomly, without any pattern, where if you know, okay, this guy went here and this guy went here and this guy went here, that does not help you to predict where the next guy will go. That's what I mean by randomized. If you do that kind of method, then it's the best approach, and it's actually very good. It just works if you do big samples, and so that's why you have the large-scale clinical trials for vaccines and things like this. Are we good up to here? Or just let me know if you're not. Okay.
Good so far.
Good, okay. And then here's question 8. So the dean of a college would like to determine the feelings of students concerning a new registration fee that would be used to upgrade the recreational facilities. All students would pay it. That's an important sentence. All the students would pay it. Which of the data collection plans would provide the best representation of the students' opinions at the school, and which students? I mean, it's got to be all students because they're all going to pay the fee. Okay. What's wrong with A, where you just survey the students as they enter the recreational facility between 1 to 5? Well, I mean, they use the facility every day. You know, they're more willing than other people to pay the fee, or at least they might be. All those people who never use the facility are completely shut out. You're not going to get their opinion. They might be less willing to pay the fee. So, you know, this one's biased in a way that's just really, really blatant. Some kinds of bias, maybe you can't get rid of, like the left-handed thing, probably in many situations makes absolutely no difference. You know, but it still counts as bias, whether it matters or not. This one, it's not only, you know, it is not only present, it's not only bias, but it's bias that matters. That's two separate things. Okay. C, what's wrong? See, now that's more subtle, but C has two problems. First, you only reach people who read the newspaper. Okay. Might matter, might not, but it still counts as bias. The worst thing is you get something called voluntary response bias. The only people who will take the time to fill out your survey are the ones who really care. So they're either people who use the facility a lot, so they really care, or they just really don't like the fees, so they care. But a lot of people in the middle won't answer. So this happens with voting. You get people on both sides of the split in our country. People who really care come out. You don't hear from everybody in the middle. So, okay, so no, all the methods would not be equally effective. You need to randomly select the ID numbers and send a survey to those, and you will still get voluntary response bias, even then. But at least it's better than limiting yourself to people who read the paper. Now, how do you cope with the voluntary response bias? Well, so to some extent, that gets outside of mathematics. Because everything we do is based on these theorems about probabilities that assume you randomly selected 1,000 M&M candies from the vat. All the samples, all groups of 1,000 candies were equally likely to be the selected group. And then you weighed them. So you got the weights right, or at least you know within plus or minus, you know the accuracy of each weight of each M&M. They didn't get to decide whether or not to answer your survey. You know, statistics is like as true as any other part of mathematics. You know, it just kind of is, almost sort of by definition. You count things and it has to be this way. But what happens when you do a survey? People are free to answer or not answer. And then you have to try to compensate for that. And that gets sort of outside mathematics a little bit. And they do things like they have focus groups and try to figure out, well, with all those people who did not answer, if you could somehow induce them to answer, you know, then which way would they go? Or compare maybe in past elections after the fact, you got what you had from the survey, you got what really happened, you try to compare and see, okay, some kind of adjustment process. It gets very fancy. And I mean, they collect data about it. It's still data-based. They still are able to talk probabilities, but it becomes much more indirect and less reliable. You know, for physics, this stuff is perfect. Just perfect. So I'll leave it at that. So back over to...
I actually had a question about that question.
Yeah, sure.
I mean, that was the answer I said, and it makes sense to me why that's so. But I did notice that the sample sizes were different for each one. And
that part doesn't matter. And yeah, thanks for bringing that up, because a lot of people say you compensate for that in formulas that we'll learn.
Okay, yeah, I guess that was kind of my question.
But,
like, is there like an I mean, because like, you know, if
bigger
you
samples are always better. But yeah, there was a question. I think it was not number 8. Maybe it was a different one where like they were. I think in the story they were doing everything right with you get one big pool and then you randomly assign to 2 different treatments, but you didn't. You know, you didn't do equal numbers in the 2 groups, and but everything else was okay. And so, and in that part, I think maybe that was sort of an unfair question for this homework. I'll make a note to do something about that, because it would be easy to think that it matters, but it'll turn out to be, you know, the formulas compensate for that.
Sure. Well, I was actually more wondering, because at some point it will matter. Like if you randomly sampled like 3 people like that, you know.
What it does is on one group you have a big wide margin of error.
Okay.
On the other group you have a narrower margin of error. But then you do some arithmetic that puts the 2 margins of error together, and you get it. So for the difference, the margin of error for the difference between the 2 averages, the 2 means, the margin of error for the result of subtracting is even bigger than the margin of error for either one of them alone. And so you end up just making this great big margin of error that compensates for all that uncertainty on one of the groups.
Right. If you're talking about if it was a very small sample size.
Yeah. And so you say, okay, the difference was this much, but the margin of error is so much bigger. They differed by 5, but the margin of error was 20. So we don't know if they really differed or not.
Okay. All right, thank you.
Yeah. Okay. So I think that's about it. If there was anything that you guys wanted to bring up else at the project sampling, or there's data collection for the project. You know, for those people who see this video but haven't gone through, you know, looking at the modules yet, in Module 6, you'll need to watch, you know, my video on how to collect your sample. And these others, the public domain ones, I think are helpful, but you know, the book, the textbook, the OLI textbook also covers it pretty well. So that's for Module 6. But then back to about Module 7, which we're just coming in too soon, and you may want to preview. You may be getting nervous about, well, but what is this project? You got me collecting data from it, but what am I going to do? And there's a Module 7. There's the mini lectures on that, and there's a thing in the workbook. It's not an assignment, but you need to read it. Module 7, Topic 1 really lays out what the project is about. And so, you know, you can do everything in Module 6 without knowing. And some of the instructions when you come to Module 7 will sort of only make sense if you've done the stuff in Module 6. In Module 6, I have you go ahead and collect the data and make the graphs. We learned how to do the graphs by hand in Module 4. And we also learned to do them in Excel in Module 4. And so you take all your techniques from Module 4 and you apply those to your own data, but you don't have to write any kind of a paper in Module 6. You just practice the things we learned from Module 4 on your own data. And then you come to Module 7 and there will be instructions for how to write a paper about this. If you want to jump ahead a little and maybe read that module, that Topic 1 in Module 7 that describes the big picture of the project, it's harmless. So you could go ahead and do that. And I'll probably be adding a few items to Module 7 over the next couple of days, a few extra videos and things like that. I'll add this video. And okay, I think that's about it. Did you guys have anything else before I close it off? Okay. So we'll see you next time.